Chapter 10, Counting Methods and Probability. We're going to start off the chapter with 10.1, applying the fundamental counting principle and looking at permutations. The fundamental counting principle. If one event can occur m number of ways, and another event can say occurred n number of ways, then the number of ways both can occur is found by taking the product, m times n. And this will always be true if you're picking just one from each of those events. For example, you are framing a picture. The frames are available in 12 different styles. Each style is available in 55 different colors. You also want a blue mat board, which is available in 11 different shades of blue. How many different ways could you frame your picture? If we want one style of frame, and we want one color, and there are different, we want a mat for it, a type of blue mat, one mat board. There we go. If we want one of each of those, our choices, there are quite a lot. There are 12 styles to pick from, so we can have any one of those. And within that style, there are 55 colors to pick from, which sounds like a lot, but it's actually quite true. And then if you have 11 different mat boards to pick from to kind of go around that picture frame, there's a total of 7,260 different ways you could frame your picture. That's a lot. Let's try another interpretation. It says Manuel wants to advertise the number of one-topping pizzas he offers to his customers. Create a tree diagram to determine how many different one-topping pizzas are available at Manuel's Pizzeria. So a tree diagram is ultimately going to be like that fundamental counting principle. If you want to order a pizza, that would be the top of the tree. That's something that you're not going to have the choice on. You're just going to get a pizza. So from there, you want to figure out different things on this little chart on the right. You can choose the size of your pizza, you can choose the crust, and you can choose the topping. So to create a tree diagram for this, notice there are two sizes to pick from. So I'm going to split the pizza apart into a large pizza or a medium pizza. And then it says choose a crust, and there are two types of crust, deep dish or thin. For your large pizza, then you could have a deep dish or a thin. So I'll just go DD for deep dish and then thin. You could have a medium and do the same thing, deep dish or thin. Then you're going to choose your one topping, and there are 3 choices for those. So if you have a large deep dish, you could have sausage, pepperoni, or cheese. So I'm just going to go S, P, and C. You could do the thin and have the same options, sausage, pepperoni, or cheese. If you had the medium deep dish, sausage, pepperoni, or cheese. Medium thin, sausage, pepperoni, or cheese. Now the choices at the very bottom are how many different ways you could order a one-topping pizza. There's SPC 4 different times. 4 times 3 would be 12. This means there are 12 different one-topping pizzas that you could order at this pizzeria. So 12 different one-topping pizzas. For this next example, I would hope that you can change a couple of things for me. This is an old template for the notes. We've had this happen before, and I didn't get the license plate picture to show up on the video, but it's in your note packet. But because of that, we actually have 3 numbers followed by 3 letters. So if you'd flip-flop those words around, that would be great. It says the standard configuration of a Minnesota license plate is 3, then add numbers followed by 3 letters. So if we think about all the possible numbers we could put on a license plate, technically each individual digit, you have 10 choices, 0 through 9. So I'm just going to write 0 through 9. There are 10, that's a 9, boy, there we go. There are 10 digits to pick from, 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Letters of the alphabet, there are 26 letters to pick from. This is going to be significant when we talk about all the different ways we could kind of arrange those to make a license plate. We have 2 scenarios here, A and B. How many different license plates are possible if letters and digits can be repeated? So you could have 111 AAA, you could have 123 ABC. Those would all be unique configurations. The easiest way to do this is to just draw a line to represent each location on the license plate. We have 3 digits followed by 3 letters. Now, if you can repeat them, that means you have 10 choices for each number that you want to have on your license plate. They could be different, they could be the same, it won't matter. For letters, you could have 26 choices for each location. And then this is like the fundamental counting principle. If you want 1 at each location, we're going to multiply all those together. 10 times 10 times 10 times 26 times 26 times 26. Go ahead and enter that into your calculator right now. 10 times 10 times 10 times 26 times 26 times 26. There are over 17,576,000. That's how many different license plates could be made. And that's not even including like specialty license plates or anything like that. That's just including plain letters and numbers. But it's modified when we cannot repeat. It says how many different license plates are possible if digits and letters cannot be repeated. So we're still going to have kind of that same setup. We have 3 digits followed by 3 letters. Here's where we have to think about, well, if we can pick anything we want for that first number. We have 10 digits possible. But whatever number we select, we can't pick that again. So how many digits would be possible for that second location? Only 9. And then if we pick that second number, there are only 8 choices for that third spot. Now let's apply that to the letters as well. We could pick any one of the 26 letters of the alphabet for that first spot, but then when we select that, we can't choose it again. So then we only get 25, and then there's only 24 spots left for that third location. And again, applying that fundamental counting principle, if we want just 1 at each of those unique locations, our answer is quite small, but still a decent size. 11,232,000 different license plates. So it will depend in the directions if you say that things can be repeated or if they can't. A big definition that will apply throughout this chapter is called a permutation, an ordering of n number of objects. So here's an example of what a permutation will look like. How many ways can you arrange the letters A, B, and C? If we're using all 3 letters, we could have the order go A, B, C. What else could we do? I could flip-flop the C and the B, and I could have A, C, B. That's a different order. We could put B first and have B, A, C, or we could have B, C, A. We could put C first and have C, A, B, or we could have C, B, A. How many different ways could we arrange just those 3 letters? It looks like there are 6 ways. All right, so let's see. To make that easier, what if we had 7 letters and we wanted to rearrange all those? It would take a long time to list them out. So the factorial button on your calculator is going to be a useful tool for you. It's just an exclamation point. N means you're ordering any number of objects, like for our case we had 3 letters. So when you have that exclamation point, that really is an exclamation point, I promise. All right, let's try that again. If you have an exclamation point, like n, you read that as n factorial. It means you're taking that number n times something less than that, times one more less than that, all the way down till you get to the last value, which would be a 1. That's a times right there. So you're just kind of multiplying everything from that number down to the number 1. For example, if you have those 3 letters again, 3 factorial means you'd start with the number 3, go down 1 less to 2, down 1 less, and then you get to 1. So if you do 3 times 2 times 1, that means there are 6 ways to rearrange all of those letters into unique orders. And if you look up above, we had 6 unique ways. So this works for smaller amounts for n, but even bigger amounts as well. It says 10 teams are competing in the final round of the Olympic bobsledding competition. How many different ways can all 10 teams finish the competition? Assuming there are no ties, and that would be kind of like that example B, it says that. If every team finishes in a unique place, that would be 10 factorial, which means you're going to take 10 times 9 times 8 times 7, all the way down till you get to 1. Oopsie, I forgot the 3. Can't forget about the team who finishes in that location. So 3 and then 2 and then 1. You can enter that all into your calculator, or if you remember where the factorial button is, you can type 10 and then have that exclamation point show up. Either way, you're going to get 3,628,800 different ways all 10 teams could finish in that bobsledding competition. Seems like that's a lot, but it quite actually is. Now it says, let's get more specific. In how many ways can the gold, silver, and bronze medals be given, assuming there are no ties? So now we're not quite as concerned about every team. We just want the gold, silver, and bronze medals. So we want the top 3 teams. If we think about location, we've got gold times all the teams who could finish for silver times all the teams who could finish for bronze. Well, technically, all 10 teams have an option for winning the gold medal. Could be any one of those 10 teams. But the team who wins gold means there is one less for the silver place. So that would be 9. And then for the bronze medals, there are 8 teams that could finish there. Notice we're not using all of that factorial option, just the first 3. And if we multiply those 3 together, there are only 720 ways that gold, silver, and bronze medals could be awarded. We can make that process more efficient by another definition. If we take the permutation of n objects taken r at a time, this will help alleviate writing out all the choices. It's called NPR. And if you notice where your exclamation point was on your calculator, there's an NPR next to it. The definition is n factorial over n minus r factorial. The n would be the total choices that you have to pick from. N minus r, so we divide out the values that we're actually not looking to have a permutation for. So n is the total choices, and r would be how many you're actually wanting to choose. So let's rethink that gold, silver, and bronze again. Remember, there are 10 total teams to pick from, but the medals only take 3 places out of all 10. Therefore, the permutation formula, which will give us the same result when we wrote it out one at a time, would be 10 factorial divided by 10 minus 3 factorial. And 10 minus 3 is 7. So that means we're dividing out all the placeholders beyond that bronze medal position. This by definition is 10 times 9 times 8 times 7, 6, 5, 4, 3, 2, and 1. But if we divide out 7 and lower, so 7 times 6 times 5 times 4, 3, 2, and 1, notice everything cancels except for that 10 times 9 times 8, which was 720. So on your calculator, you should be able to enter this in. Type the 10, and then get that NPR to show up, and then type 3 and press enter. And we should hopefully get 720 ways again. So that NPR rule is the same as the definition, but on your calculator, it makes it more efficient. Be careful in the directions for your homework. If the homework just says evaluate, you can type it into your calculator. If it says show the definition, you get to write this fraction rule out. So let's try with just our calculator. I know these 3 examples are on that slide up above, so just work with trying to fit. You have more space than I do, so that's good. To evaluate 6p5, what this means is we would be taking 6 factorial divided by 6 minus 5 factorial, which is just 6 factorial over 1 factorial, which means it's really going to be 6 times 5 times 4 times 3 times 2 times 1. But type this into your calculator, 6, and then the NPR button, and then 5, and press enter. And that's the same as 6 times 5 times 4 all the way down to 1. You should get 720 different ways. That's how many ways if you have 5 or 6 things and you want to arrange 5 of them in a unique permutation order. 10p2, same idea, 10 factorial over 10 minus 2 factorial. If you enter this into your calculator, you should get 90 ways. And then 4p4, if you have 4 items and you want to arrange all 4 of them, that simply becomes 4 factorial. 4 times 3 times 2 times 1 is 24 different ways. So again, make sure that you can enter that into your calculator and also be able to define it using the definition up above. The last thing that we'll do with the permutation definition is called permutations with repetition. And what this means is you are going to still order things but maybe some of your choices match up. So if you show them in a unique order, it would be hard to tell that they're different. So here's how this works. It still looks like the fraction we did up above, only we've got some things that we're going to divide out at the bottom. So N means the total objects or choices you have to pick from, but S means anything that repeats itself, like letters in a word. This is really the only time we'll use this form of a permutation. Find the number of distinguishable permutations of the letters in each word. So the first word is I, E-Y-E. How many different ways could we actually rewrite this letter or this word to look different? We could do E-Y-E, we could do E-E-Y, and we could do Y-E-E. Anything else, even if that first E and that last E are kind of flip-flopped, is going to look like one of those three choices. So here's how the definition works. There are 3 letters, so N equals 3. There are 2 letters that repeat, so that's your S. By definition then, we have 3 factorial divided by, there's only 1 repetition letter, so that would be 2 factorial. Please type that into your calculator, 3 factorial divided by 2 factorial. And you should get 3 distinguishable permutations. So I'm just going to write dist perm. There we go. There are 3 different ways we could rearrange the letters in the word I. Let's go ahead and try Minnesota. If we count up all the letters in Minnesota, there are 9 of them. That means N equals 9. That equals. N equals 9. There we go. Now if you look at anything that repeats itself, the letter N itself does repeat. So that would be our distinguishable permutation. It repeats itself 2 times. So there are 2 letters that match up. To create the number of possible permutations without having to write them all out, we can do 9 factorial, all the ways the 9 letters could be rearranged, but divide out any time the 2 N's are in the same spot. This is equal to 181,440 distinguishable permutations. Thankfully, we don't have to list those all out. That would be a lot. All right, how about Panama? The word Panama has 6 letters total. And notice the letter A is represented 3 times. So that means there are 3 letters that are exactly the same when we try to rearrange that order. For the number of distinguishable permutations then, we'll take 6 factorial divided by 3 factorial. And that gives us 120 total distinguishable permutations. We have to end with a pretty unique example, so let's look at Mississippi. There are lots of letters in Mississippi and lots of letters that repeat themselves. If we count up all the letters, there are a total of 11. So there are 11 letters to pick from. But notice there are several that repeat themselves. So for the S, we have 4 I's, so there are 4 letters alone that repeat themselves, 4 S's, and 2 P's. There are 3 different sets of repeating letters. That means up above when we have our definition, notice how the denominator could have a parenthesis. You're definitely going to need that here. If we do 11 factorial divided by all the repetition, it's important to note here that they go in parentheses. So we're going to have a 4 factorial, another 4 factorial, and 2 factorial. Please type this into your calculator for sure. We want to make sure that if there's more than 1 letter that repeats, we recognize the need for the parenthesis and we can all get the same end result. Even with all that repetition, there are 34,650 unique ways we could rearrange the letters in the word Mississippi. So 34,650 distinguishable permutations. And that's lesson 10.1.